Hey everybody, welcome back. Today I want to talk about some applications of Euler's formula. I'm going to call this talk buy one, get 1,000 free. Absolutely incredible stuff. So with one formula, you can derive most of the popular trig formulas that you'd need. It's incredible. But first we have to talk about some important ideas from complex numbers. And so here I'm just going to give you the very, very basics. And so the first thing I want to recall is the imaginary unit I. So recall that I is equal to the square root of -1. And then we said before that I squared was equal to -1. And of course, we can carry this out. We mentioned before that this turns out to be cyclic, right? That means the pattern cycles. Okay, and two, I want to talk about complex numbers. So let's talk about these in the complex plane. So this complex plane we denote by C bar. This, which is typically known as the x-axis in R2, this will be the real axis. And this right here, which is typically known as the y-axis in R2, we're going to call that the imaginary axis. Okay, so we think of a complex number as this combination, so a plus bi, and we really think about it as sort of, you can think about it as an ordered pair, a comma b, but we also like to think about it as a vector. And so the length of the complex number, how long it is, that's called its modulus. And the angle from the positive real axis, that's theta. Sometimes that's called the argument. And so some things we want to note are the following. So when I say I want the real part of a plus bi, I essentially just want the portion of the term that doesn't have the imaginary unit. So in this case, the real part, the portion without the imaginary unit would be a. So yeah, if I call for the real part, just looking for a. Now, if I ask for the imaginary part, I just want the bit or bits that are attached to I. So if I want the imaginary part of a plus bi, I'm looking for exactly b. It's sort of like saying, what's the x value? Well, the x value is a. What's the y value? The y value is b. And so just for a quick example, if I asked you, well, what's the real part of 3 plus 4i? Of course, you would say 3. And then if I asked what's the imaginary part of 3 plus 4i, you would say 4. Note that we don't say 4i. The imaginary part is strictly 4. Again, it's like saying what's the y value. Oh, we could do this in a more of an algebraic realm. So say I wanted the real part of x squared plus 2i xy plus y squared. Well, I'm essentially looking for the terms that don't have an I. So the real part would be x squared plus y squared. And if I want the imaginary part of this, I want exactly what's attached to I. So that would be 2xy. Okay, so with that said, we want to recall something else. So of course, let's recall Euler's formula. We proved that in the previous video, so let's recall. So for any theta that's real or complex, we have e to the I theta is equal to the cosine of theta plus I sine of theta. And we're going to use this formula today. So the whole point of today is to use this to generate a bunch of classic trig formulas, formulas that you may have forgotten. In fact, let's go ahead. Let's use this to find the double angle formulas for sine and cosine. It's really, really neat. So let's say our goal is to use Euler's formula to find, let's say we want the cosine of a double angle and the sine of a double angle. And so how is this going to be helpful? Well, let's see. So for Euler's formula, we have e to the I. Well, not e to the I theta. The angle that we're concerned with now is 2 theta. So we just plug 2 theta in for theta. So e to the I 2 theta. We can rewrite that algebraically. That's the same thing as e to the I theta quantity squared, right? If you think about your exponent rules in algebra, that's just fine. But then by Euler's formula, what is this equal to? Do you remember? That's exactly cosine of theta plus I sine of theta. So by a substitution, we get the following. So this is exactly cosine of theta plus I sine of theta, quantity squared. And we're just going to carefully square this out. So that'll be the first term squared. So that's cosine squared of theta. And then double the product of the inside. Right? So if I double the product of the inside, that's exactly 2I cosine of theta sine of theta. And now I have to be careful because the last term comes about from squaring this. Well, if I square this, I'm going to get an I squared sine of theta. In fact, just for the sake of clarity, let's put that in and then we'll deal with the I squared. But if you recall, I squared is exactly -1, so we need to take care of that. Okay, well, I've got a bunch of terms. How is that helpful? Well, it's helpful if you recall the following. So recall, maybe I'll say now we recall. One. So cosine of 2 theta is exactly, actually, let's talk about it. So if I look here, is cosine the real or the imaginary part? Well, it's not attached to the I, right? So I'm looking inside of here. Well, it's not attached to I, so cosine is the real part. So this will be the real part of e to the I 2 theta. Okay, so what is that? What is the real part of that? Well, if I want the real part, so I look here, the real part contains the terms without I. So the real part has this and this. The real part won't have this because this has the imaginary unit I in there. So we want exactly this and this for the real part, but that's exactly cosine squared of theta minus the sine squared of theta. And so that gives you your formula for the cosine of a double angle. So you know that from trig class, and if you forgot, you can always rederive it using Euler's formula. So cool. Well, this one's a buy one get one free because we can also get the sine of a double angle here pretty easily, right? So sine, if I look back inside of here, right? If I look inside of here, does sine go with the imaginary of the real part? Sine goes with the imaginary part because it's attached to the I. So sine is exactly the imaginary part of e to the I 2 theta. But what is the imaginary part? Well, the imaginary part of e to the I 2 theta is here without the I. So that'll be 2 cosine of theta sine of theta. So there's your double angle formula for sine. So cool. Truly a beautiful formula is Euler's formula. Another thing that's fantastic is, say you needed the sine of a triple angle. You needed sine of 3 theta, or sine of 4 theta, or sine of 5 theta, etc. You can just keep using Euler's formula. So yeah, if I needed, let's say I needed sine 5 theta for a problem, hypothetically, I plug 5 theta in here, and this just becomes raised to the 5th power. I can use binomial expansion and then take the imaginary part, and that'll give me the sine of 5 theta. Okay, so say, for example, now that you wanted the sum of angles formulas for sine and cosine. So now we want, let's say we want the cosine of a plus b and the sine of a plus b. So again, we're going to use Euler's formula. So Euler's formula, so for all theta, e to the I theta is equal to the cosine of theta plus I sine of theta. And remember, the real part of this is cosine, and the imaginary part of this would be sine. Okay, so how do I find these sum of angle formulas? Well, it's pretty neat. Euler to the rescue. Here we go. Check this out. So e to the I, whatever the angle is that you want, that goes in for theta for Euler's formula. And then we're going to use some algebra, so distribute the I. So you've got e IA plus IB power. And then let's split this up, because I know that the sum of exponents can be expressed as the product of bases. So it's e to the IA, e to the IB. Well, that's great, because we know that we can use Euler's formula to express this just by plugging a in for theta. And we can use Euler's formula to express this just by plugging b in for theta. So that seems really, really cool. So if I plug a in for theta, so this would be equal to cosine of a plus I sine of a. Now if I plug b in for theta, this would be equal to cosine of b plus I sine of b. Okay, so now we're just going to use some algebra, some distributive property in the classic way. So maybe I'll give myself some room here. What do we have here? It looks like cosine of a times the cosine of b plus I cosine of a sine of b, right? This times this is this. And then I just distribute here as well. So this will give me, it looks like I sine of a cosine of b. I times I is I squared, but we recognize that as minus 1, right? I squared is minus 1. So then sine A times sine B. Okay, so now we're sort of hip to the process. We know that the real part will go with cosine, and the imaginary part will go with sine. And so that means that the cosine of A plus B is exactly the real part of e to the I A plus B. But that's exactly this term and this term, right? This is real, and this is real, because there's no imaginary unit. So that's cosine A, cosine B, minus sine A, sine B. And there's your formula for the cosine of the sum of angles. So that's really, really cool. And for free, practically for free, we also get the sine of the sum of angles. Now remember, sine goes with the imaginary part. So this will be the imaginary part of e to the I a plus b. And so that'll be this part, the portion without the I, and then this part, the portion without the I. So that'll be the cosine of A sine of B plus sine of A cosine of B. This one I'm going to rewrite because typically it's written with this term first and this term second. It doesn't matter because addition is commutative, and so it's multiplication here. But it's more typical maybe to see this. So just switching the order. Sine of A plus B is sine of A cosine of B plus cosine of A sine of B. How cool is that? Euler to the rescue again. Also keep in mind, you could also find the cosine of A minus B and the sine of A minus B. It's just a little bit more algebra. That'd be a good exercise. So now let's prove the odd and even function rules for sine and cosine using Euler. So we're going to say we want to show that for all real x, or let's use theta just to be maybe consistent. So for all real theta, sine of negative theta equals the negative sine of theta. And also that the cosine of negative theta equals the cosine of theta. So in this way, we say that sine is an odd function, right? It has origin symmetry, so in the real plane. And then cosine is an even function. It has y-axis symmetry in the real R2, the real plane. Okay, so how do we start? Just look at the angle, right? Let's start with this. Let's start with e to the I negative theta. But using algebra, that's the same thing as e to the negative I theta. And we know what negative exponents do. That's going to send that downstairs. And so by Euler's formula, we know what this is equal to. So by Euler's formula, this is 1 over cosine of theta plus I sine of theta. But it might be helpful since we've got a complex object down in the denominator to multiply by the conjugate. So let's multiply by the conjugate. So that's cosine of theta minus I sine of theta. And that's over cosine of theta minus I sine of theta. So effectively, I've just multiplied by a useful form of 1, but this conjugate can be helpful in transforming this into a nicer form. So let's see what happens. We're going to multiply conjugates here. So the numerator should be, so 1 times anything is just it's the other thing, right? So that'll be cosine of theta minus I sine of theta. And then when I multiply here, when I multiply conjugates, complex conjugates, I should get a squared plus b squared. So you can check that and convince yourself that you do get the plus with complex conjugates. Well, that seems pretty cool because I know that cosine squared of theta plus sine squared of theta is 1. In fact, so we've proved this using a right triangle in a previous video. After this, let's prove this using Euler's formula. I think that'd be pretty neat. So that's cosine of theta minus I sine of theta. So what does that mean for us? That means that, well, we wrote sine first. Let's do that. So sine of minus theta is equal to the imaginary part of e to the minus I theta, which is equal to, and if it's helpful, you might want to rewrite this. You don't have to, but if it's helpful, you could rewrite this in this way. And so that you can say, oh, well, the imaginary part should be the minus sine of theta. And that proves it. And so the cosine of minus theta, well, that of course should be the real part of e to the minus I theta. And the real part of this, so if I look at the terms, well, this is clearly the real part. And this, the minus included, would be the imaginary part. In fact, I could even rewrite this as cosine of theta. What do I want to write this? Plus I times minus sine of theta. So then you can really see the imaginary part and the real part. Okay, so yeah, as we said, cosine of minus theta is exactly the real part of this, and the real part is cosine of theta. And there's your even function rule for cosine and your odd function rule for sine proven. So cool. Isn't that awesome? I love this formula. So now, sort of as a little bonus, let's prove that classic Pythagorean identity that this is equal to 1. Right, that's equal to 1. So we want to prove for all theta, cosine squared of theta plus sine squared of theta equals 1. So how are we going to do this with Euler's formula? We're going to be kind of clever. So we're going to start with the 1 and show that we generate this on the left. Okay, so 1, a way to represent 1 in a clever, useful way is to say that's e to the I theta times e to the minus I theta. And that's helpful because, you know, when you multiply the same base, you keep the base the same, you add the exponents. Well, the exponent's going to be 0, so that really is 1. Another way to think about this is if I rewrite this as a fraction, it's really this over itself. And so by Euler's formula, we have a representation for each of these, right? So by Euler's formula, Euler says that this is equal to the cosine of theta plus I sine of theta. And then this is the cosine of minus theta plus the I sine of minus theta. And we know how to deal with that. And so we prove that cosine's an even function and sine's an odd function. So that's going to give me the cosine of theta. And this will be minus I sine of theta, again, since sine is an odd function. And then you can just distribute this out, right? So you can multiply your cosine of theta over both terms. And then, of course, your I sine of theta over both terms here. So cosine times cosine is cosine squared of theta. And then what do we have here? We've got this minus I sine theta cosine theta. So that's that times that. Then I multiply here and I get a positive I sine theta cosine theta. And then I multiply here and that's going to give me minus I squared sine squared of theta. Well, the middle, that makes me happy. These cancel. These are gone. And remember, what is I squared? I squared is equal to minus 1. So you're going to have minus minus 1. So that's equal to cosine of theta plus, cosine squared of theta plus sine squared of theta. So that gives you a second proof in this channel of this Pythagorean identity. So cool.